through this kind of process of subduction and generation of volcanoes, we have the so-called ring of fire all around the Pacific, in the western United States, in Central America, and the western part of the of South America, and of course allusions to here to New Zealand. Galapagos is very different. It's similar to Hawaii, but about this some other time. Due to this kind of distribution of plate boundaries, we have different plates. These are the most important ones. Of course, there are many more plates, and I will give you also a paper to read through about the many microplates we have. And one of them we're going to talk, that's not very known. There are only 2 papers about this. I don't know why, but it's the Galapagos microplate, which is on the northwestern side of the Galapagos Islands. And about the Galapagos origin, we're going to talk also a lot, because in your guide there's not that much information. You will see what I'm talking about. Now, what is also important for us here, and now for you here on this hotel, is the third type of plate boundary, which is a transform plate boundary, like this one. Okay, the other ones we discussed anyway. Of course, any kind of movement provokes seismic activity. And we have the primary wave, we have the secondary wave, we have the love wave, and we have the, therefore I will give it to you in PowerPoint, otherwise in PDF you are not going to see this. And the air wave, and there are 2 more, but what I want to tell you here is that we have the problem that the distribution of the plates here gives us a lot of headache. And you are here only one night, but we never know when it's going to happen, what's going to happen. When we talk about the different plates here, we talk about the Nazca plate, the Cocos, the Pacific plate, and here's of course one missing, we're going to see it soon. And we have here on the continent another 2 plates, the Caribbean and the South American. And here we have the East Pacific Rise, which is a divergent plate boundary, the Galapagos Spreading Center, also a divergent plate boundary. Here the Nazca South American Trench, which is a convergent plate boundary, and therefore, because the Nazca plate goes below the South American continent, we have the different volcanoes here. But we have the problem also that the South American continent is divided into 2 continental plates. And they are separated by a transform plate boundary. The same thing like San Andres fault. Absolutely the same. But there it's called just San Andres fault. And here it's called Guayaquil Caracas mega fault. That means we have here a much bigger issue than the people have in Los Angeles and San Francisco. Now if we see a little bit in detail, this is our own. I publish a lot of things for the public. So many of the graphics you're going to see, you have never seen, you will never see, except if you buy in the future when we publish in 100 years in the next books or so. So these things are showing a little more in detail what is going on. The same thing like before, a little bit separated from each other, seeing the movement of the plates, and here this kind of movement. Here the Galapagos, and here we have the other thing which we're going to talk about by tomorrow and in the next days. Not now. But here we have a triple junction of plates, the Cocos, the Nazca, and the Pacific plate. And then we have another microplate which is also important for some other considerations for the Galapagos. But what is important is this thing here, the transform plate boundary of the Caribbean plate and the South American plate. And this of course something we can see. It was called up to 2004 the Dolores Guayaquil mega fault or mega shear, but it has been changed because the Dolores fault system in Venezuela has nothing to do with the whole fault system, so it's now renamed in Guayaquil, Caracas. Now here what you can see are different years when we have had a very huge earthquake along this fault. And the last one, and this is the problem, was 1859. Now if the last one was 1859, let me see where it comes, I will see it soon, after the pizza, is that we have a certain reoccurrence. As you know, with piloseismic research, we could find out what is the real reoccurrence of this reactivation of this fault. As we have only data of the last 500 years, so the only thing we can say is that we have every 100 years we have a big earthquake here in Quito. We talk about Quito, and this is a very vulnerable zone. This hotel is very vulnerable, just in case. And it's followed by another one 10 years later. So I will make up now the data, so the reoccurrence is clear. 1500 an earthquake, 1510, 1610, 1620, 1720, 1730, and so on. The last one was 1859, and this is a big problem. I will show you why. We'll make an experiment with you. You take your You go this way, I go this way. You stay. No.
You go this way.
No. You go there. Now we accumulate energy, and the longer we accumulate, the longer we wait, the bigger is the release and form of an earthquake afterwards. So we are waiting here now 150 years for something we should have had 50 years ago, and this is a big problem. So why I'm showing this with a pizza and with this shrimp is that it's a superficial phenomenon, the transform fault. That means there's no warning time. There are warning systems for earthquakes in Japan when there's a signal of the primary wave and you can stop gas lines, the metro and so on. We don't have this kind of advantage here at all. This goes through Quito. Here we are right now exactly here, okay? And the fault is this way and so on and so on. Here's another excellent volcano. Here's my university here in the valley. And here's another volcanic complex of 5 volcanoes, of which one is active and 4 are not active. So the faults you can see here, they go through the city. Here's the city. And here's the new airport.
Right.
Here a little bit about the systematic I was saying. Now this is not counting that much because these are not earthquakes which happened here in Quito itself. They were been felt here, there was damage here, but they were very far from here. And this is the 1987 earthquake close to a volcano called Reventador. Now you may think we have the best civil engineers and architects here in Ecuador of the world because they built wherever. But this is criminal and they don't follow the rules. We have a seismic code and they don't follow it. Just to give you an idea, here is an intersection from the valley to the city. We are very close, we are somewhere here. Here's the hotel, you can look to this. And the highway collapsed in 2000. It collapsed because we are built up here on ashes. There's no rock here, there's no lava. Everything is on pyroclastic material.
Wow.
So it collapsed. It just collapsed, like this. And then, you know what they did? They made a tunnel. So from the worst to the even worse. Okay? And the tunnel is somewhere here. And you can see here, this is not even elastic, this bridge, and so on and so on. And they put here some cement in order to restrain that these people can build high and high and so on. The other thing is, you have another hazard here, which I should not refer to, but still, some 2 months ago, crashed here another airplane, like on the corner here, and this was like the 5th airplane in the last 15 years. There's fog here and nobody can see something. This is exactly the route of the planes and so on. But anyway, what's going to happen, and this is a problem, this is a picture from El Salvador in 2001 from the big earthquake 7.1 with 800 people died, is, as I say always, as Richter said, earthquakes do not kill people, collapsing buildings do. And there are other secondary effects like these landslides due to the earthquakes which kill people. And this is a similar photo I could take here very close to our university because this is the same material and almost the same view like in El Salvador. Saying or implying that the same what happened there can happen here in a worse manner. This from Japan, this also, and this you know, Kobe 95. And this is some of the issues we check now, the seismic resistance of bridges and buildings and so on. We do a big work now here because people are more and more aware that they need to know and they need to prevent. Bless you. This is Taiwan. The center of the building was made by trash. They saved a lot of money at that time and they lost everything afterwards. This building is seismic resistant, just in case. Seismic resistant meaning that it's gonna bound, but the outer parts, as you know, they're not that safe. That means you're going to have a lot of problems with the glass, windows, and stuff like this, and even with the cover of the building. But the building's not going to collapse. This one is one of the very less which are safe. When I talk about very less, I should give you some data. I made a study in 2004. We made also, and we made many things. So I can give you always some more input. Not now. Maybe in the bus. We have a very good seismic code, but nobody follows it. So in 2004, I found out that less than 0.2% of the buildings in Quito are seismic resistant. Less than 0.2%. 99.8%, and this number is decreasing because we build more and more, but not seismic resistant.
Because it's more expensive.
No, it's not. This is the joke. People don't get it. But every civil engineer and every architect will tell you, oh, I have to do something special, so I have to charge you more, which is a lie. It's a lie. Now, people are aware of this. They give many conferences to high levels, and they save money building seismo-resistant. So do I, at this right moment. This is from India. Unofficially, 100,000 people who died. And I always say to my students and to all the conferences, this could be you. This is a picture from BAM. 1 year before the tsunami accident was on the same day in Iran, and a big earthquake. Now this you know, and here a little bit the same overview like before. Here's Quito. We're going to drive today down to the valley. We're going to pass a few very nice volcanoes. Here are some of them, and here are some of them. And then we're going to go up here to the northern part and see some stuff here of the Laos distractions and the Lions landscape here. Please interrupt me whenever you want, okay?
What causes the valley then? Why on the east and the west do we have all this activity?
This is another conference, but I will give you a very short explanation. What we think happened here is the following. When you take plastiline and you put it between two forces, whatever it is, okay, and you have compression, then you should have compressive faults. It's normal, it's logical. But at the same time, when you compress, the same stuff gets up there and extends. And this is what we think. It's extension dynamics through compression. Now, what I explain is always the following fact. Everybody has done a hot dog in his or her life. Okay, so you know what I'm talking about when I tell you. You take a piece of bread, and then you cut it in half. Then you have two halves, and then you put some ketchup and mayonnaise and so on, and then you put the sausage, and then you close it. Let's call it like this: close it. And then you want to take a bite, and what happens is, then the sausage gets out, and it's on the bottom, and the dog eats it. Okay. That's what happens usually. And this same thing happens here, right now here. You know that we have extensional dynamics between Africa and South America since more than 125 million years when they got separated. Now, here's Africa, and here's South America. So in the Atlantic, we have a divergent plate boundary. That means South America goes towards west. Okay. At the same time, we have here the Nazca plate, which goes to the east. And in between, we have the Caribbean plate, which is the sausage. So this escapes towards there. Now here, exactly here, this is the Caribbean plate. So this is sausage, which is pressed by these two forces, and this goes up there. So at the same time, we have here, exactly here, in fact, here, we have a transform fault boundary, and at the same time we have this kind of thing. So we have an escape mechanism, a compressive mechanism, and extension mechanism at the same time. And therefore we can see all the nice faults here very close by Quito with my students. I just go around Quito and we see fantastic stuff, and today also. So you're going to see some of the very nice things. So Cotopaxi is one of the volcanoes we're going to see today. We have many more. We have here from Quito. This could be also almost we are right now here somewhere. This is the volcanic complex of Pichincha, and we have the dome activity of volcano called crystal volcano. Okay, so when people tell you here in Quito, almost everybody in Ecuador, there are only two volcanoes. One is called Guagua Pichincha, the one is called Ruco Pichincha. This is not really true. There are five, and the one which is active is this part here. They have been so much active that it was taken to manipulate the whole public here, as we have had the worst economic crisis in 98, 99, as an issue that this was more important than to talk about the other stuff, but about this or some other day.